morning, everyone. First of all, many thanks to Professor Slapper for inviting me to deliver this talk. I will present a class of problems known as pattern matching problems, and we will discuss certain issues, in particular parallel algorithms for these problems. Pattern matching problem is, the classical pattern matching problem is very easy to define. Given an array, P called the pattern, and another array, P called the text, we look for all occurrences of the pattern in the text. So these arrays, P and T, clearly may be either one-dimensional, two-dimensional, or higher-dimensional arrays. So there are numerous results, both theoretical and applications, most of them for strings. So to my knowledge, the active research on such topics has started in the middle of the last century and continues nowadays. A part of this basic problem of pattern matching, there are many related problems which can also be classified as pattern matching problems. In particular, identifying various patterns, motifs, or any kind of peculiar features in a text. In solving such problems, usually pattern matching, the original one which was in the previous slide, are used as subroutines. Major applications are found in computational biology, because clearly a string can model a biosequence, and there are various applications of one-dimensional algorithms for pattern matching problems. Of special importance are problems for detecting repetitions of certain portions of the text. They are interesting both from point of view of combinatorials on words and pattern matching. And so the first works are listed here, so you see there they date back to the beginning of the last century. So I will mention about these works later, after introducing some notions. In particular, discovering repetitions is applicable to data compression, because clearly we find many occurrences of the same pattern in the text, or repetitive occurrences. We can just record at the beginning of the repetition and one copy of the repeating text, and then just memorize the starting points of the other occurrences without recording the entire pattern. More recently, somewhere in the 90s, so this research was extended to two-dimensional arrays. So here, text and patterns can be regarded as bitmap images represented by matrices of pixels and stored in a database. So here the natural applications are in pattern recognition, low-level image processing, computer vision, and more recently in multimedia. So clearly in pattern recognition and other related disciplines, we often look for some appearances of an image within a scene, and such algorithms are applicable to solving such problems. efficient solutions to such problems rest heavily on studying periodicities of the given arrays. So in strings, periodicity is very easy to define. So here are two small examples. For instance, in the upper string, ABC is the period because it appears consecutively in the string. So the last one may be incomplete. And here the period is ABC, while the second one is non-periodic. We may assume that we have a vector of length 3, so starting from letter A and with tail at C, and so we can generate all the sequence by shifting this repetitive pattern over the sequence. So in 2 dimensions, defining periodicity is not so trivial, and actually it took a couple of decades to arrive at a reasonable definition of periodicity which can be used for algorithms. And these are to me the 2 first papers which introduced two-dimensional periodicities. If in 1D we can think that we have one vector, so it's very trivial here. We may have different types of periodicity. For example, we may have 2 periods in 2 linearly independent directions, and we may have a non-periodic array. Of course, we may have line periodic 2-dimensional array where periodicity is possible only in one direction, but not in 2 directions. So the first one is called a lattice periodic, and there is one more, radian periodic. And the classification and the understanding and the proof that these are the only possible and reasonable definitions of periodicity turned out to be a non-trivial problem. So, combinatorial pattern matching problems have been studied under different settings and computation models. Of course, sequential algorithms came first. After that, there are online algorithms, real-time algorithms, where we have a fixed amount of time within which we have to accomplish some task. We have algorithms using only a constant number of extra space and related in-place algorithms. We have also parallel algorithms. And in this talk, I will focus more on parallel computation for pattern matching problems. So I chose this topic first because I think that parallel approach, parallel algorithms are quite natural for not only for pattern matching problems, but for in imaging in general, unlike with other problems where using parallelization looks a bit artificial. Also, my opinion is that non-trivial parallel algorithms are underrepresented in our community. I mean, people who attend this conference and IWCI, occasionally some parallel algorithms occur, and the algorithms which I will discuss here are a bit different type. So in the rest of my talk, first I will very briefly recall some basic notions, concepts, and facts related to parallel computation, which I will use in the rest of the talk. And I will illustrate how such algorithms are designed in the considered class of problems. On one example, a problem which I worked on some years ago. So now, very briefly, I know that most of you are familiar with the parallel computation and related concepts. But I'm sure also that maybe a few people are not. So here, parallel, we consider parallel random access memory machine, theoretical. So this is a general, natural generalization of the RAM machine. We have here shared memory cells. We have processors. Each processor can be viewed as a RAM with a private local memory. Processors communicate via shared memory. We have a computation step which may be either read, compute, and write type. So the read phase, here we may read from a shared memory. So any processor can read from the shared memory cell. In the compute phase, the processor can perform local operation, and in the write phase, it's possible for processors to write on shared memory cells. Here, an important issue is how to resolve the write conflict. There are a number of models, most popular, which are common arbitrary and priority models. The priority model is the most powerful one. The weakest is common model, which means any algorithm and any theoretical result which applies for the common model applies also for the other models. And the example which I will consider is under the common model, which means that it's valid for any other model. So this is basically the so-called concurrent read, concurrent write RAM model. So here we have some specific notions with parallel algorithms. So we may speak about optimally fast algorithm. So this notion is not that trivial to define as with sequential algorithms, but I think intuitively it's clear. So if several processors work simultaneously, this is considered as one single time step, and we count the number of distinct time steps from the beginning of the computation to its termination. On the other hand, we can speak about optimal algorithms, which is a different notion from optimally fast. Before that, work of a parallel algorithm is the product of the number of processors and the running time which is used to find the result. So if we have, let's say, m processors, and if the overall running time is n, then the work will be m times n. A parallel algorithm is called optimal if its work equals the running time of the fastest possible sequential algorithm for the considered problem. especially in this area of combinatorial pattern matching, designing optimally fast algorithms is a major issue. And also for sequential algorithms, not only for parallel algorithms. Because, so this is related to complexity issues, clearly, and in complexity theory, usually for many combinatorial problems, we are interested in if they are, say, NP-complete, or if they admit polynomial solutions. Here, this is usually out of interest, because for most of the considered problems, we immediately have naive polynomial algorithms of not very high complexity, say quadratic or cubic computation time algorithms. And here, the issue is how to improve them, and how to obtain possibly the best possible algorithm among all algorithms that may exist for the problem. So both regarding optimally fast and optimal with so these are major issues. Later in my talk, I will refer to two fundamental results. The first one is known as Brandt's lemma. You can see the true relation. So this is a classic result in parallel algorithms. And later I will refer to this theory. Another fundamental result is the so-called Fisher, H, and Wilkerson algorithm. You see here what it can do. In particular, it can be used to determine the first occurrence of a string in another string. This is the purpose for which it is used in the example to consider later. In constant time. So this is interesting. If we have n processors, and if we have, let's say, n numbers or string of length n, so we can perform this search in constant time. And now to the example, I will need a few preliminary notions. So I think the slides are easily readable, just a couple of lines on each. You can see what a primitive word is. Basically, the primitive word is just a counter example is the word ABC, ABC. So this word is non-primitive because it doesn't satisfy the definition. While if we cannot partition the word in the identical copies of the same string, then it is non-primitive. And square in a string is two consecutive occurrences of the same primitive word. And here, back to these two papers which are cited at the beginning, Thue proved that there are arbitrarily long square-free strings over alphabet of 3 symbols or more. For 2 symbols, clearly, we cannot have arbitrarily long square free strings. For example, if we have alphabet A and B, if I write A, to avoid square, I have to put here B. So if I right than B, I will have a square. So I have to put here another A. And now if I put A, we'll have a square here. If I put B, now I will have once again a square. So it's trivial that we cannot have square strings over two-letter alphabet. While for 3 letters we can design a very long string in which we have no squares. So if you notice, so the papers are pretty long. One of them 20 pages, the other one nearly 70 pages, which is not very usual for papers at that time. So now usually we have long papers. 100 years ago, papers were short, which means that this is a non-trivial result. So here we can distinguish between 2 problems. Find the square in a string, or test if the string has no squares. This problem was found relevant to problems of biosequence analysis and also data compression. I commented already about data compression for biosequence analysis. Once again, people who know more about biological problems, they claim that, say, in biological sequence, it's important where information is duplicated for purposes of, say, resistance to mutations, etc. So this problem of finding squares in a string has some relevance to computational biology. And here are a few known results. You see, first of all, a string of length n can contain n log n different squares. Note that the number of squares can be more than the length of the string itself. So because some squares can overlap, so we may have n log n squares in a string of length n. So these are, for example, Fibonacci strings, which are defined similarly to Fibonacci sequences, which are very well known to everyone. Also, all such squares can be found in time proportional to the number of squares. So, and clearly, these algorithms are optimal. Here are the people who contributed to solving this problem, among others. And also, at the bottom, you see the result about optimal parallel algorithm for the problem. With Alberto Apostolico, we tried to extend these investigations to 2 dimensions, and in a series of papers we designed optimal and optimally fast algorithms for both for detection and for testing if an array is tandem free. So here we use a different term because squares is reserved for strings. So both sequential and parallel algorithms for this problem. Now briefly some preliminaries which will be used in the sketch of the algorithm. So here we assume that our arrays, these are arrays of symbols, of arbitrarily many symbols. So you may think that we have scene with and image, which is the or pattern, which have arbitrarily many colors. These are not binary arrays or binary strings. By the way, it was a major issue how to design, say, optimal algorithms for strings with arbitrarily many letters in the alphabet. Alphabet-independent algorithms, and it has taken maybe 10-15 years to arrive eventually at an algorithm which solves this problem. In the estimation of the running time, the size of the alphabet doesn't appear. So a block is any rectangular subarray of a given array. We call array primitive, so this is extension of generalization of the notion of square. So we call array primitive if it cannot be partitioned in this way. This X cannot be subdivided into identical copies of a block, double. And also we can speak about vertical and horizontally primitive arrays. The definition is clear. And tandem, we call tandem such a shape of two neighboring blocks, primitive blocks, either which touch each other, either at the side or a corner. So we consider two different types of tandems. Each of these rectangles is called the root of the tandem. Clearly, we have a tandem if it's a simultaneously vertical and horizontal tandem. What is how many tandems can we have in an array? So this theorem answers this question. So for tandems of the first type, we may have n cube log n tandems, and for type 2 tandems, we may have n to the 4th tandems, where the logarithm is with base 5, where this is the golden ratio. Again, in the proof of this theorem, Fibonacci strings, so we design arrays using Fibonacci strings. Just to say what Fibonacci string is. So we start with two letters, A and B. A is the first Fibonacci word, B is the second one. Then AB is the third one. Then BAB is the next one. Then AB, BAB is the next one. So similarly to designing the Fibonacci sequence of numbers, we can design Fibonacci string. And you know that Fibonacci sequences are used to design hardest possible examples when we to obtain lower bounds for running time of algorithms, let's say in combinatorial optimization. While Fibonacci strings are used in designing hardest possible examples in pattern matching. And this is one of the results, optimally fast algorithm for detecting all possible squares, all possible tandems in an array. They are optimal because their work matches the possible number of tandems in the array. clearly we cannot do better than this. To discover all tandems, we have to identify them all. And if there are this many, so we need at least this many work. In the design of the algorithm, we use first the already mentioned Pitch-Reg-Wiggerson algorithm, and the optimally fast parallel two-dimensional pattern matching algorithm. Designed by 8 authors, so we can find all occurrences of a pattern, two-dimensional pattern, in an array in log m time with this many processors, n squared over log m processors. So our algorithm consists of, and this is, I'm saying our algorithm, but most of the algorithms in combinatorial pattern matching have a similar structure. They have a pre-processing phase, and in which we extract some useful information about the given pattern. And then, in the search phase, we use this information for fast search. So here, basically, in the pre-processing phase, a table is generated called the table of witnesses, which is useful for which is used in the search phase. The idea of the search phase is the following. So we look for tandems. Let's consider the first type of tandems. So first we generate all possible repetitions, not necessarily tandems. And then for each of them we check if it is a tandem or not, which means we check if the root W is a primitive block or not. More into detail, so here there are some preliminary settings which are technical, and I don't think the time would be sufficient to go through them. So we basically consider here we consider stages. So this is the search phase already, which is organized into stages. The number of stages is basically the logarithm of the size of the array. So here we use kind of binary search, binary subdividing of the array, and this is typical for divide and conquer strategy. So for each stage, given a stage, we subdivide the array into these many blocks, and after that we look for repetitions which have size compatible with the sizes of the blocks, and also somehow related to the block. For example, the leftmost root is fully contained in the block, so once a repetition is fixed, then we first test if it appears to be a horizontal tandem and then vertical tandem. So the two verifications are not symmetric, and this is based on numerous lemmas constructions, etc., which cannot be discussed here. So if I do, it will be pretty boring, I think, just to show you why I'm saying this. So this is one of the papers where so here there are some preliminaries which basically I showed already, and here we have stages, and now we start the horizontal round, which is given a repetition, given two consecutive occurrences of the same block, checking if this is a tandem, if this is if the roots are primitive. Here there are many difficulties, many cases, sub-cases. So this is the analysis of the horizontal search. So we need several lemmas which are given here in the paper without proofs, but they are not so trivial. Then we have, once we know that this is a horizontal tandem, then we start the vertical round to see if it is vertically primitive. Here this round is, as I said, non-symmetric. We need some preparation, different cases. Finally, we come to certification, etc. Now let me go back to the slide. It's not difficult to test if some occurrence of two consecutive blocks is a tandem, that the roots are primitive. The difficulty is how to do all this with a small amount of work, so that eventually we obtain an optimal algorithm. Otherwise, to find all occurrences of tandems, it may be a quiz question for 10 minutes. So the difficulty is to do it in the best possible way. And in sum, finally, we prove that a sub-stage can be computed with this amount of work. So all stages are performed simultaneously, in parallel, all stages and sub-stages, and we have to take care that the overall amount of time when we have all processors working doesn't lead to huge amount of work. A huge amount of work. So now towards algorithms time and work analysis. So the pre-processing phase takes this time, log n time and n squared work. So this is, as I said, in the pre-processing phase, we use algorithm which was designed by Cole and also their algorithm for finding weaknesses of a given array. And it has these parameters. After that, with stages, when we go to stages, every stage is computed in constant time, because there we use the search phase of their algorithm numerous time for many purposes, multiple uses of solving pattern matching problem which I defined at the beginning of my talk. And multiple uses of this basic, this constant time Fitch, Wedge and Wittgerson algorithm. So the search phase is executed in constant time. How about the work? The work will be the sum of the work of all the stages and sub-stages. Stage number eta 1, eta 2, as I already mentioned, takes this amount of work, and we have this many sub-stages. So now we have to sum up, and we arrive eventually at this upper bound for the work performed to solve the problem. Okay, so now we can use the Brent's lemma. By Brent's lemma, we can slow down the time of the search phase, which is constant, but we can make it non-constant. We can make it log n, keeping the same amount of work. And thus, overall, the solution would take log n time and n cube log n work with this many processors. So if you see the number of processors is very high, so if n is a big number, probably we cannot have in practice this many processors, but we can take a smaller number of processors. So if we take, let's say, n square processors, then the running time will be n log n instead of double logarithm. If we take one processor just, we can make this algorithm sequential using, once again, Brent's lemma, then it will have running time n cube log n. And we won't speak about work then. So, and this will be still optimal sequential algorithm. Why is it optimal? Because the overall work of the algorithm matches the lower bound of the number of tandems. That's why it is optimal. Clearly, we cannot detect all tandems with work smaller than their number. So, about the time complexity, log n matches the time complexity of the optimal apostolic Breslauer algorithm for testing square freedom of strings. So clearly, the one-dimensional problem is a particular case of the two-dimensional problem. Also, testing square freedom is clearly not harder than detecting all possible squares, because if detection was easier, then we would detect all squares and see if there are squares or not. And since the running time of our algorithm matches the optimal running time of this easier problem, then it turns out that it is optimal. As a last remark related to these problems of detection of squares, testing square freedom, etc., etc. So here on this slide, a comparison is given between the one-dimensional and the two-dimensional cases. We can see that there is a difference because which to me is interesting. So here in 1D, the problem about squares, this is the optimal time and work to test if a string contains any squares. And it takes exactly the same time and work to detect all squares. While in 2 dimensions, it's not so. To test, so the time is the same in both. But the work to test if an array is tandem free takes n squared log n time. So if we compare with the work to detect all squares, if you see here, it's bigger. This is for tandems of type 1. For tandems of type 2, this is the optimal, this is the work with which we can test if there are tandems. Well, this is the work we need to detect all tandems, and this is optimal. So this cannot be improved, which means that in 2D, the two problems of testing and detecting are essentially different with respect to their time and work, while in 1D they are equivalent, which at least to me is interesting. And finally, possible applications. Once again, this detection of all tandems can be used, is potentially usable for data comparison. So we were intending to try to use this, use our algorithms to design a data compression algorithm for arrays. Unfortunately, we didn't find time to do it. But maybe in the future. Also, I think that this approach can be used in the so-called digital geometry. So digital planes, for example, are a major issue in digital geometry community. In IWCIA conference, half of the papers are about digital planes and digital lines. And so if we can, digital planes can be represented as arrays, and it's interesting that arrays representing digital planes, they feature these periodicities which exist theoretically in the definition of two-dimensional periodicity. For example, if we consider digital or discrete plane with integer coefficients, there we have we can detect patterns which periodically appear, and we can cover all the discrete plane with the same patch, which is which has a shape of parallelepiped, digital discrete parallelepiped, and these features lattice periodicity. This is if we consider planes with rational coefficients. If we consider digital planes with irrational coefficients, then they are either non-periodic or they may be line periodic, which is the other type of two-dimensional periodicity. So we may have a plane with irrational coefficients, and still in that plane we may have a rational line on which we have integer points over the line, and so we can have a period over this line. And if we take a bounded region, then we can picture even the fourth type of periodicity. And to me it would be interesting to investigate this, how a structure of digital planes align with these fundamental notions of periodicity which were introduced in pattern matching. And hopefully, and also as I have written in this last paragraph, I have discussed with some people whose research is focused on digital planes. They believe that such approach can lead to designing a truly two-dimensional algorithm for digital plane recognition. I think that this was the information I wanted to communicate to you. Thank you very much for your attention.
Thanks, Professor Brimkov. Have you got any question? Something. So, as far as I see, you find exact matches. So when the pattern and the covered text are the same.
They are not the same, but
somehow similar.
We have a text, let's say, a big array, and we have a pattern. And we look for occurrences of this pattern inside the text. So this is the basic pattern matching problem, which I mentioned at the beginning.
And can your methods modify to find more or less similar matches?
Approximate, you mean? Yes, there are such results for approximate pattern matching. I have been interested only in exact pattern matching, but I read a couple of papers in which there was an approximation which probably makes sense for some practical applications. There were algorithms, and I think even not so recently, methods were designed, for instance, to detect a face, say at the stadium. You have a picture of some criminal for which you look for, and you scan the public and look for the face. And clearly exact pattern matching probably is not possible because the person may have changed a little or may move some of his nose, or then we should have a means to approximately match the pattern on the image. So I have read about such results, but these are not mine.
Excellent. Have you got any further comments or questions? If not, thanks again.
I could also thank the speaker to give him some small salary to remind him your visit and this nice talk.
Thank you very much.
And